Hello there. This is Dr. Dell talking, and I want to talk to you today about the number systems that we should be teaching our students and the order in which we should teach it and the difference between them and so forth. Now, to do this video, I created 4 documents, and you can have them in the PDF below, and you should have hopefully already downloaded them and printed them out so that as you follow along, you can refer to these documents with me. And I just simply want to discuss with you these number systems and some of the things that I believe that any teacher should have in mind and know about when one is teaching them. Well, first of all, I've used different letters to designate the different number systems. There's N for natural numbers, there's Z for integers, Q for rational numbers, R for real numbers, and C for complex numbers. And this is normally the sequence of number systems as you teach them to students. I put in a couple other, 4 other actually. Over here you have the positive rationals. Here you have the algebraic numbers, which I'll tell you about in a minute. Here you have the hyperreals, and here you have the hypercomplex. But the main number systems we teach are on this vertical line. And I want to tell you what those are. Now, on this sheet here, we talk about the properties of numbers. And different number systems, as we climb this ladder, have different sets of properties. There's actually 12 properties here that I've indicated, and I'll be talking about them as we go along here in a minute. And then on this sheet, I've actually put a description of these number systems. Now, the N stands for what are called the natural numbers, and these are simply the counting numbers, 1, 2, 3, 4, 5, etc. This is the first thing we teach our children when they're very, very young. And of course, we also then teach them when they're pretty young how to add these numbers and how to multiply these numbers. And those operations, addition and multiplication, satisfy certain properties. One of them is called the associative property for addition, and that just means it doesn't matter the order in which you add numbers. And the same is true for multiplication. You can do it in any order and you're going to get the same result. And indeed, the commutative property, which means you can add a plus b or b plus a, you get the same result. Ditto for multiplication. And then the distributive property. And I'm assuming that you know all of this. This is a review certainly for you if you're interested in teaching math, because this is all covered at a very elementary level. Now, also in the case of the natural number system where we have multiplication, we learn that multiplying a number times 1 equals the same number, and that's called the identity, the multiplicative identity, and 1 is the multiplicative identity for the natural numbers. In the counting numbers, the natural numbers, we haven't introduced 0 yet, so we don't have property 6, which is the additive identity. And we don't, of course, have negative numbers, and we don't have reciprocals or multiplicative inverses yet, not in the natural numbers. So the first thing we teach our kids then is the natural number system. And of course, pretty early on, we have to get into the concept of the decimal number system, and I'm going to assume that you understand that. That is a marvelous invention that lets us then count numbers any size we want to, and I'm going to assume you know the decimal system. Now, pretty early on, we need to introduce the concept of 0. Our ancestors struggled with this for some time, but they finally got the idea that, yeah, 0 needed to represent a number, even though it represented the absence of something. And it wasn't too long that they realized you needed a concept of negative numbers. And so if you take all the natural numbers, and for every one of those you have a negative number, then you have the what are called the integers. And again, the integers satisfy the same properties that the natural numbers did, plus some more. You now have an additive identity, that's property 6, and you have additive inverses, that is property 8. In other words, if you take 5 and add to it minus 5, you get 0. Now, what you don't have with the integers is you don't have the concept of multiplicative inverse. So that is something that you have to create another number system to do. Our ancestors actually, and I put this off to the side, going back to the time of the Greeks, before they struggled with 0 and negative numbers, they had the idea of fractions. So I indicate that Q plus would just be the positive rational numbers, the positive fractions, and I've indicated that here. P over Q, where Q is not 0 and P and Q are natural numbers. This would be the positive rationals. But actually today, we usually, and it's good pedagogically to do this, we usually introduce 0 and the negative numbers along at the same time we're introducing fractions. And so the rational numbers are both positive and negative, and they have fractions. and that would be the rational numbers. And it turns out that if you express those in a decimal expansion, it will be a repeating decimal expansion. That's easy to prove or demonstrate, and that's usually done, and you've probably done that at a pretty early level. Now, in the foundation course, where we're teaching math for to beginners to get them started and get them grounded, and it's the math you need for ordinary practical mathematics. We go up through and use these rational numbers. This is something you can use with a calculator. Every measurement you ever take of anything will be a rational number, and so you will deal with that with a calculator, and you'll deal with these properties and learn how to use these properties. Now, the plot thickens. It turns out, and our ancestors discovered, that there are numbers that are not rational that we need to deal with, at least on a theoretical basis. From this point on up, this is where we now begin to get into math on a theoretical basis from this point up. And what they discovered is that you can think of it conceptually as what would happen if you take all decimals, those that repeat and those that do not repeat, all decimals. And the answer is then you would have what we call the real numbers. And the real numbers now, at first we treat them intuitively, and that's how they should be treated in the middle and high school level until you get way beyond, well, really beyond calculus. You treat them intuitively. You just say the rationals are all repeating decimals, and then you add in all the non-repeating decimals. You have the reals, and you correspond them to a number line, the real number line. And this set of numbers is called the continuum. And quite frankly, this is not discussed usually very rigorously at the high school level, and properly so. It's really too deep for it to be done then, because the property that you've added when you go from rationals to reals is not really an algebraic property at all. It is really what mathematicians call an analytical property or a topological property. It's completing the number system in an analytical sense. And the best and easiest way to explain that, if you want to, is what's called the least upper bound property. If you have a bounded set of numbers with an upper bound, will it have a least upper bound? In the case of rationals, the answer is no. For example, if you take all numbers whose square is less than 2, and then take that set of numbers, then what would be its least upper bound? Well, the least upper bound would be the square root of 2. But the Greeks proved that that was not a rational number. In fact, that was a crisis for the Greeks when they proved that. They took two lines that were perpendicular of length 1, and they looked at the hypotenuse, which would be the square root of 2 according to the Pythagorean theorem, and they demonstrated this was not rational. And by the way, it really threw Greek mathematicians into a real tither, because they had their mathematics and their philosophy combined, and they thought this was the only thing you needed to describe the world, and then they discovered there's a number here that they needed, a theoretical number that's not rational, and it really bothered them a great deal. And in fact, they retreated from the number concept for a long time. And our ancestors didn't begin to wrestle with these things until the 1700s and 1800s. And they did it intuitively at first. They said, well, the reals are all decimals, not just the repeating ones, but they didn't really understand this completeness property, property number 10, until the 1800s, believe it or not. It was in the mid-1800s that they finally treated the real number system in a rigorous way and began to really understand what it was all about. Now, as a matter of fact, when you start looking at the solutions of polynomials, not only do you get the square root of 2, but you get something called the square root of -1, and that really threw them into a tizzy, because this is not a rational number, and in fact, you can't even think of it as, it won't even be on the real number line, and so they call this an imaginary number, which is a terrible name by modern standards, but to them it was imaginary, it didn't exist. Well, it's just as real as a real number. It's a theoretical construct, just like real numbers are. And what it turns out to be, the real number system corresponds to a straight line, and the complex numbers, when you extend up to that, corresponds to the plane. Complex numbers are simply correspond to points in a plane. So you have the complex plane. You have the real number line, and you have the complex plane. So this is a real number line. This is the complex plane. And this is what I talk about extensively in Tier 4. Remember, We teach math in a tiered level. That's how I believe that it's most successfully taught, and it's how I've taught it for a long time, most successfully. And so we only cover up through the rationals in the first two tiers, the practical math foundation. We begin to talk about the real numbers in tier 3. We begin to talk about the fact that there's uh, irrational numbers and imaginary numbers, and then we actually do it in a fairly rigorous way. It's intuitive still, but in a thorough way in tier 4 in the last pre-calculus course, just before we go into calculus. So these are the number systems that we have. Now it turns out that the complex number system has another property that the real number system does not have, and that is it is what is called algebraically closed. Any polynomial with complex coefficients can be factored into linear factors, whereas you cannot make that statement for real numbers. So property number 11, algebraically closed. All polynomials factor completely into linear factors. That is something that's true of complex numbers. It's not true of real numbers. Now, this becomes critically important in science and engineering, because what happens in science and engineering is you are able to convert certain mathematical models into polynomials, and you need to factor them into linear factors. That is particularly useful in differential equations when you use something called the Laplace transform, for example. And it turns out that these complex numbers have wonderful interpretations in our physical models. In fact, it's so important to teach complex numbers in high school in preparation for calculus and engineering and science and so forth, because they're going to be used extensively in engineering pretty early on. So that's why I cover them in tier 4 at that first level. Now, another interesting story in the history of numbers and the development of numbers is way back in the day of the Greeks. They did consider something called infinitesimals. And an infinitesimal is a number that is not 0, but it is greater than, or pardon me, it is less than any ordinary real number. So property number 12 is the infinitesimal property. That is, there are non-zero numbers that are smaller than any ordinary real number. And the Greeks believed that and used it. And then in the 1600s and 1700s, this was used widely by the inventors of calculus and differential equations. It started with Isaac Newton and Leibniz, and then later extended by Euler. And so mathematicians were using infinitesimals in their arguments for calculus back then, very early in the game in the 17 and 1800s. But in the 1800s, finally, mathematicians decided to make this concept of real number system rigorous. They wanted to know exactly what axioms it satisfied and how could you start with the rationals and build the reals. And they did that. We do that in tier 7 and 8. Well, what happened was when you went from the rationals to the reals and you did it rigorously, the infinitesimals weren't there. They didn't appear anywhere. And so our ancestors in the mid-1800s decided, well, there just are no such things as infinitesimals. They were handling the so-called imaginary numbers because they extended that to the complex, and they did that rigorously. So all the way up through here was rigorous. You got all the way up to here, the complex numbers in the 1800s. And of course, like I said, this is vitally, critically important in science and engineering today, and that's why we want to bring our students right up to here in a heuristic way. This is heuristic from here to here, meaning it's not rigorous. Then when you begin to do the theory, you have to give up infinitesimals, at least they did for a while. But it turns out, believe it or not, in the 1960s, they figured out a way to extend the reals to what are called the hyperreals. And in the hyperreals, you have infinitesimals again. In the 1960s, for crying out loud. That's less than 50 years ago. So in the 1960s, a guy named Abraham Robinson did it using something called ultrafilters. And it's a wonderful story. And this is something I do not teach in the tiers. I believe this probably needs to be done. Well, actually, I discuss it somewhat in tiers 8 and 9. But just to show how that can be done, because the construction to go from reals to hyperreals is actually not any harder than to go from rationals to reals. This is a tough construction. To do rigorously from rationals to reals isn't easy. You can use Dedekind cuts or Cauchy sequences. I found a way to do it with actually decimal expansions that I've never seen published anywhere. And then it's not much harder then to do another similar thing. But men didn't figure it out until the 1960s. And then I'm presuming that there's something called hypercomplex, although I personally have never gone to that level. I've not had a need to explore that. I've stopped really at this level here. So that's what the number systems are all about, and I believe that you should teach up through here using a calculator for practical math. Make sure that they're very familiar with rational numbers. You should discuss the real numbers. We do it in tier 3 and 4 in a heuristic way and correspond to the real number line. In tier 4, we then go on up to complex numbers in the complex plane. All this is done, well, I'll say heuristically rigorous, if you'll allow me that. It's not theoretically rigorous. We don't do theory until tiers, and we only do the theory for the future professional mathematicians. Engineers and scientists don't need to know the rigor of the theory. And then we do that in tiers 7, 8, 9, and we also discuss the hyperreals. So these are the number systems I think you should know about if you're going to be teaching math to high school level students. And I hope this has been interesting and enlightening. And I will see you then on another video. This is Dr. Dell. Have a great day. Bye-bye.